Hello community! Today we talk about here a fusion of LLMs and knowledge graph, the next step. So, we have some brand new research today and it is beautiful because we're gonna improve AI reasoning on knowledge graph. And yesterday we defined here structure within our Monte Carlo tree search master algorithm and this fast thinking on graph for GRAG for GraphRAG optimization. But today we go a step further. So let's open up this video and here we go. You remember our beautiful models DeepSeek R1, OpenAI R1 or Gemini Thinking. They have here pre-trained supervised fine-tuning, reinforcement learning, inference or test time computation. For advanced reasoning it takes 2 minutes maybe when they are thinking. And the idea is if the parametric knowledge within our LLMs is not enough, we just connect here to external data that are stored in a knowledge graph. So whenever the LLM decides, hey, I need more data, we have GRAG. And yeah, this is exactly the video of today. So what are we talking about today? There is a new idea. Up until now, the LLM, either function call or tool use or whatever, and we regarded here the knowledge graph simply as an external data source. And we just had to call it, extract it, and done. However, a knowledge graph, if you look at it in its entirety, is so much more beautiful, so much more powerful that we can use. So let's explore what we can do with this. And everything was just fine, Everything was fine until in the morning, and I got here this mail from AWS, and they say, hey, 27th of January, this is for me today, recording this video, we are introducing now the GraphRAG toolkit on Amazon. And I said, unbelievable, just a day after I had my video on GraphRAG optimization, and they give you here all the formula and everything that you need, and you have here the GitHub repo, great. And then I started to read all 212 technical abstracts of all the AI papers that were published today. And there was a spark. Suddenly I noticed there is something happening. And you know what? The spark, I noticed it a little bit yesterday. Remember when we were reasoning with knowledge graph and agents? And I taught you about if we have a knowledge graph and we can identify communities on this graph, we already started to redesign our knowledge graph into knowledge communities. And today we just go further. Think about this. Let's say we have here 3 different ideas how to optimize a knowledge graph integration into LLMs. Brand new ideas. There's a trend, reading the scientific paper of today, that we have some new hybrid AI architectures where our knowledge graph and our LLMs are not treated as independent components, but are now more deeply integrated, and actually they are mutually reinforcing systems. So LLMs are no longer yet just a consumer of a knowledge graph, but they are actively involved in the knowledge graph refinement, in the knowledge graph reasoning, and in the knowledge graph error mitigation. And this is what we are going to talk about today. So let's come here to the core idea. Let's say an LLM plays here a critical role in restoring here the context lost in a knowledge graph during the build-up of the knowledge graph. How does it happen when converting here unstructured text into entity relation triples of our knowledge graph? Often, a lot of important semantic details are simply omitted, are not integrated. And the LLM now retrieves the original textual context associated with those particular triples that were selected given my query to the LLM, thereby enriching now the knowledge graph with more precise information, and this is a methodology we call triple context restoration on the knowledge graph. But you know what? We also have the other feedback loop. And during the reasoning task answering complex queries here, the LLM uses here particular subgraphs that were identified and retrieved from the knowledge graph. However, when the key information is missing in these subgraphs, we have now a new query-driven feedback mechanism that simply identifies the gap that we have in the subgraphs of our knowledge graph, allowing now the system to dynamically update our knowledge graph. You see what we have? We have a perfect feedback loop. The LLM is trying to build a better knowledge graph given the particular query the LLM is receiving. There is a simple example. Beautiful. So now let's come to the fact, and I know you want to see the literature on this. Absolutely. So this is from yesterday, January 26, 2025. We have here mitigate information loss in knowledge graphs for GraphRAG, and this is exactly what we're going to look at. We have here a new framework which restores the semantic context associated with the triples in a knowledge graph, and we will employ here a query-driven feedback mechanism to iteratively enrich the original data in the knowledge graph with new data, thereby significantly also enhancing now the LLM reasoning capabilities whenever the LLM is retrieving subgraphs from the knowledge graph. We face two problems. Let's have a look at this. Very simple. Now here on the left side we have a text. Albert Einstein, German-born theoretical physicist, beautiful, best known for developing the theory of relativity. He received a Nobel Prize in Physics, especially for the discovery of the law of the photoelectric effect. But you know, now we have something that is interesting. Everybody knows the theory of relativity, Albert Einstein, but the Nobel Prize in Physics 1921 he received for the photoelectric effect. And hardly anybody knows this. And as you can see here, from this text, the knowledge graph extraction, the buildup of a knowledge graph, simply misses here the link. So if you ask, hey, what did Einstein win the Nobel Prize for? The theory of relativity or the photoelectric effect? In the knowledge graph, we do not have an edge. We do not have a connection. So we have simply dependencies that are missing due to a context loss that we had in the semantic sentence over here. Plus, given an information sparsity, this occurs when incomplete extraction results in a failure to meet the query requirement. So, question, what is Einstein's most famous achievement? Now, this is a trick question, no? Is it a Nobel Prize in Physics? That hardly anybody knows, but this is a significant effect. Or is it for the theory of relativity that everybody knows? So what is here the most famous achievement? And there's now here a missing extraction here, what it is best known for. So we do have problems in the knowledge graph. And now we set out to solve this. Solve this in conjunction with our LLM. Now you might say, hey, wait a minute. If I would take this sentence and I would think about the video that I did just 2 days ago about the fact decomposition here, that I take here a long sentence with a lot of information and I build here a fact decomposition where I only have singular, simple sentences, a lot of, and then I have a decontextualization, so every sentence can stand alone for a better buildup of a knowledge graph. Yes, this would be a gorgeous idea, but you know what? The authors of this paper had no idea that just 2 days ago I would publish here my video on this, but you, as a subscriber of this channel, you can now integrate this to build better knowledge graphs. Okay, but let's go on with the classical theory. Yeah, you see this here, but I think it's a little bit complicated. Let's go step by step. So this new framework that we have is, we build a knowledge graph, which builds here a unified knowledge graph from all the textual sources that we have. And then we have a subgraph retrieval, responsible for extracting here task relevant. If I query this LLM, so the task relevant subgraphs are now identified, composed here of potential reasoning path necessary to answer here my query. And then we have something interesting. We have the triple context restoration. So for each triple, we have a graph, head and tail. In the retrieved subgraphs, the source documents associated with the head and the tail entities are now retrieved actively for all the relevant subgraph that I have in response to my query. And this set encompasses all the documents potentially containing contextual information about the relationship between the head or the tail information. So now the system goes and says, okay, now comes a user query. This is real complex, and my original graph is not enough. My knowledge graph is not good enough. So given now the actual task that is incoming, the query that is incoming, I now start to optimize here, based on the query, a new graph structure. I built new subgraphs that are now, if you want, special expert systems on the query. And each triplet is now augmented with its associated contextual sentence from the original human sentence. So what we end up with is amazing. You have to have this idea. It's beautiful. You have your triplet and your most important sentence that defines here the context of the triplet. And then comes something interesting. Then we have this iterative reasoning with a query-driven feedback loop between the LLM and our knowledge graph, where the iterative cycle that both generates answers and identify missing knowledge, thereby refining here the knowledge graph on the fly. But let's be more precise. So what we have, the system says, hey, I have missing knowledge. I can't answer the query by the user immediately. So I identified the initial answer and the context were analyzed to identify missing information regarded for the query. So we have a delta K, and this represents the set of missing knowledge. We can formalize this as a set of sub-questions. And what we do now, that we know we can identify, the LLM tells us, hey, I have no knowledge about this technical term. I have no knowledge about this function. Now we say, okay, now we go here with a knowledge graph enrichment as the fourth step. So for each missing component that we found here in delta K, a dense retriever now interacts with the original text sources to retrieve all the relevant textual information and extract here the missing knowledge in semantic form. And then we have here, as you can see, extract triplets, where the extract triplet employs here the LLM to find and extract the correct information, resulting now in itself in triplets K corresponding exactly to the missing knowledge. And then we just update our knowledge graph. We have enhanced, we have augmented our knowledge graph with specific content for the query. Add the inference run if you want. So you can build a better knowledge graph if you know the query and you have access to the information. Amazing. I love this. Yeah, there's a new fact. There's another fact. I told you in second, beautiful January 26, 2025. This is here about a knowledge graph completion. So we are exactly in the same topic, but I found this second paper to be spot on for today, because now we do the knowledge graph completion not by going in and having here, as I just showed you here, a particular procedure, but now we are in multimodal information. So we are now multimodal knowledge graph completion task. And you know what? Our colleagues here from Beijing in China, they decided to go with a diffusion-based scheme, which is amazing. But they've chosen an old friend of us, the negative sampling scheme. You remember the negative sampling we had in my videos on BERT and sentence transformer, where we just were looking to generate and identify high-quality negative triplets, and they do so by leveraging a diffusion-based hierarchical embedding generation that progressively conditions on entities and relations as well as multimodal semantics. If you want to see the code, this is the GitHub link. As always, you find the GitHub link here. So, on the topic of a multimodal knowledge graph completion exercise, we go now to the diffusion model and we take some knowledge originally years ago we had on BERT and sentence BERT with negative triplets, and we have now a hierarchical negative sampling implementation for the knowledge graph. It is nothing special. It is exactly what we know. We have here a visual encoder, we have a textual encoder, we have here our embedding layer, positive triple, negative triple. This is just implemented, but really nicely implemented. Let me show you here the interaction between the LLM and here the second paper on a knowledge graph optimization together with an LLM. So the LLM contributes to the multimodal embeddings by processing here the textual description, processing all the visual data and the structural information within the knowledge graph. And this allows the knowledge graph to represent entities in a relation now with richer, more information by our multimodal features. There's a simple example, but it's also the other way around, no? Because the knowledge graph now provides structured multimodal data that the LLM can use for a reasoning task like answering multimodal queries. Just give here an image to an LLM and say, hey, identify the following people and tell me what they're doing and whatever. And this is now possible here with this particular knowledge graph implementation. So by leveraging here our multimodal embeddings, the LLM can now generate responses that are contextually aware and semantically diverse enough. Beautiful implementation, but I don't want to focus here on the second paper because there is, yes, you guessed it, there's now a beautiful third paper. And I thought I have to show you this because this is now a beautiful paper. This is from today, January 27, 2025, recording this video. You know what we do? We develop a multi-AI agent framework that will act on knowledge graph, and the goal of this is to enhance the error detection in the knowledge graph. And you say, unbelievable. Yeah, there's a GitHub code for you. Here you have GitHub open source. Beautiful. Also from our colleagues here at Southeast University, Nanjing in China. Plus, yes, just see here, Monash University from Australia. Hello to Down Under. They call this MUG-GET. Beautiful. This is here a novel multi-agent framework for knowledge graph error detection, MUG-GET. Beautiful. Okay. But what is so nice? Think about this. They combine now embeddings, two different embeddings, because they need different kind of information. They have a graph convolution on network embedding, and they have an LLM embedding. Let's say a Llama 2 model, or go with a Llama 3 model, doesn't matter. But these two types of embedding, each embedding has some particular information, no? Because structural are from the graph convolution network, and the semantic embeddings are from the LLM. So the GCN would process here the graph structure, our node on edges, to capture how the entities are connected, while the LLM, think about it, the LLM processes the textual semantic information related now to those entity and those relationship. If you think a little bit more mathematic, we can capture now the topology of the knowledge graph through our GCN, like which entities are connected to which other entities and through which relationship, the kind of edges, the intensity, and whatever we have. But maybe they lack here the nuanced semantic understanding that an LLM can provide. So you see what we do? I mean, the authors had this idea, combine here the interconnected topology of a knowledge graph with the semantic understanding of an LLM, and we go here in a representation of the embeddings. So easy. We concatenate now the GCN embeddings and the text embeddings together, and we create a unified embedding structure. And then, so simple, and this combined embedding is then used to fine-tune the LLM. And you know what we achieve? By doing this, the LLM is not just relying on the textual data, but also on the structural information from the knowledge graph. You see this beautiful fusion of an LLM on the information of a knowledge graph. We bring them closer together. They are now so interlinked that each element is helping each other element. And this now helps the LLM understand both the explicit relationship from the graph structure and the implicit semantics here from the text. But of course, remember that I told you the goal here is the error detection in our knowledge graphs. So if the LLM has now access to both the structural embeddings and the semantic embeddings, it can now simply better judge whether a triplet is correct or not. Let's think about this. If we have the structural embedding that shows that Paris is connected to France via the connection of capital of, this is the property, and the LLM semantic embedding confirms that this makes sense now contextually, then there's a real high probability that this triple is likely correct. You see, we're again here in the verification of the data. And now we can do something beautiful. Yes, we have up until now missed here the multi-agent system, but now we bring in 4 agents. And now those agents here, head forward, head backward, whatever you call them, doesn't matter, analyze now this particular triplet of information from different subgraph perspectives. What a simple but beautiful idea. Each agent uses now the combined embeddings, the structural embeddings and the contextualized embeddings, to assess the triple's validity. And you can have that our 4 agents have a discussion, or our 4 agents have a voting mechanism, majority voting, and then you can aggregate their perspectives of our 4 agents, leading here to a more robust error detection done by multi-agent AI agent systems. I'm loving this idea. Unbelievable. We have so many new opportunities just in one day. It's just great. Yeah, I want to show you here the interface here, the interconnect between LLM and the knowledge graph in our multi-agent framework for error detection that we're talking about. LLMs are used to analyze the semantic plausibility of triplets by evaluating now the textual and the structural context of the subgraphs. So each agent, of course, an AI agent, so at the heart of an agent is an LLM, evaluates here this particular triplet from different perspectives, head, tail, forward, and backward, whatever subgraphs you have, and then you just have a discussion of agent or a majority voting or whatever you like. Here's a simple example for you. And of course, we have the feedback. And the knowledge graph provides subgraph embeddings that serve now as structured evidence for the LLM to make informed decisions about the triplet correctness. So these embeddings integrate structural and semantic information. Isn't this an elegant but so simple methodology? We know everything about this, and the GitHub code is available for free. Okay, let's come to an end, because at the end I want to show you here a video that I really love, and it is about DeepSeek R1. But let's just start here with the summary. So what we looked at. We looked here at our LLM, and I showed you 3 different brand new AI research papers about the interface of LLM and the interconnectedness to knowledge graph. And knowledge graphs are not anymore just a passive tool that an LLM calls for external data. There is this trend that I noticed today towards here, this hybrid or this fused AI architecture, where we have our knowledge graph and our LLMs, and they are not anymore treated as independent components, but they are now deeply integrated and are really mutually reinforcing system. LLM helps to build better knowledge graph, and the knowledge graph helps here the LLM in the reasoning, and then even in the fine-tuning of the LLM. If you want here again, this is from paper 1, this is from paper 2, and this is from paper 3 if you want to have a summary. But you know what's interesting is this interplay. The interplay, the active design an LLM takes here to change the different knowledge graph here with different methodologies. Those are the 3 methodologies of today. And then we could theoretically use this, and remember we are here at inference or test time compute, to do a real special fine-tuning for our LLM, given that we know what we expect on the queries. We are working in a domain of theoretical physics or in a domain of finance or whatever you have, you're a startup company. So there's a complete new world to build outside here. What an amazing time. Of course, you remember about 2 weeks ago I did this video. There is now an interconnect between the standard supervised fine-tuning and reinforcement learning and the inference-based supervised fine-tuning and reinforcement learning. And if you want to learn more about the mathematical apparatus, this is the video for you. This was done and published by Google. Yes, and this is the video, and now just for fun. I mean, it's so nice, because I was here also working here on a presentation that I wanted to show you the latest development in knowledge graph. I've shown you this, but I also wanted to show you here, if we now integrate databases, specific databases and graph databases, how we can have even a more advanced interface to our LLMs and vision language model. But this video would be much too long and much too complicated, maybe at a later time. But therefore, I was just interrogating here DeepSeek R1, how to easily explain here in a short video here the differences if we have this interconnect of knowledge graph and graph databases. What is the difference and why and when to choose which of those elements? Enjoy this video. So I use here my old friend DeepSeek R1, and I have a simple question. Hey, I say, understanding the importance of knowledge graph. Why do we need knowledge graph when we have thousands of books and all the information in textual form in sentences? Why continue with the tool of a knowledge graph when we have long human sentences? Can you design an explanation, explore the different factors or the criteria for this, and give me your scientific judgment on the importance of knowledge graph versus databases or long text documents? Try now. And and now what I love is the thought process, the reasoning that is happening here in DeepSeek R1. And you know what? I want to show you here the reasoning, and then I'll show you the result, because you know what? For me as a person, learning here, the insight, I am at the moment more interested here in the understanding here of R1 and how R1 tackles these problems. I learn how AI learns, which is amazing that I'm not interested in the answer, but let me show you. Let me give you this feeling. So, R1 comes back and says, okay, so I need now to figure out why knowledge graphs are important when we already have books and text documents. Let me start by understanding what a knowledge graph actually is. And R1 tells me, hey, for what I remember, a knowledge graph is a way to represent information in a structured data format, using node and edges to show relationship between entities. So unlike a regular database, which might just store data in tables, a knowledge graph connects different pieces of data in a network. But why is that better than just having text? Books and documents are written in natural language, which is great for humans because we can understand the context and especially here these nuances, But for machines, processing natural language is tricky. Those machines might not get the subtleties or the relationship between the entities unless they're explicitly stated. So maybe knowledge graph help machine understand the connection better? I mean, an R1 AI system asking this question is amazing in its own point. So R1 goes on. Another thing is to consider searchability. If I have a question that requires combining information from multiple sources, a knowledge graph could link those sources together, making it easier to find an answer. If I want to know which scientists contribute to both physics and chemistry, a knowledge graph could show the connection between people, their fields, and their contribution. Whereas in text documents, I have to read through lots of material to find that particular information. Databases are structured, but they might not capture the relationship as flexible as knowledge graph. In a relation database, you have tables with predefined schemas, which can be rigid. If the data doesn't fit the schema, you have to redesign the database, which isn't always feasible. Knowledge graph, on the other hand, you can add nodes and relationship without changing the existing structure, making them more adaptable. But wait, aren't there some databases that can handle relationship well, like graph databases? Oh, R1, I really appreciate your reasoning capabilities. R1 goes on. Right, but maybe the distinction is that knowledge graphs are specifically designed for integrating diverse data sources and providing semantic context. They use ontologies and vocabularies to understand the meaning of the relationship, which helps in data integration from different domains. Then there's the aspect of inference. R1 says, knowledge graph can use reasoning to infer new information. This is an absolute fascinating thought for a machine, no? R1 continues, for example, if the graph states that A is a parent of B and B is the parent of C, it can infer that A is the grandparent of C. In textual data, that inference isn't automatic. A human has to read and connect those dots. Semantic search is another benefit. Instead of keyword matching, a knowledge graph can understand the intent behind a query. So if someone searches for books with authors who influence modern philosophy, the knowledge graph can traverse relationship between authors, their influences, and their work to provide relevant results. In contrast, a traditional search might just look for pages containing the words books, authors, influenced, and modern philosophy, which might not be as accurate. You remember in my last video I showed you about community search here on a knowledge graph manifold? This is real similar. But R1 goes on. Scalability might be a factor too. As the information grows, maintaining a knowledge graph could be more efficient than dealing with ever-expanding text documents or complex databases. The graph structure allows for an easier expansion and integration of new data sources without disrupting existing ones. But I should also consider the limitation, tells me R1. Creating a knowledge graph requires significant effort to structure the data, define the relationships, and maintain the accuracy. Text documents are easier to produce since they don't require such structuring. However, once a knowledge graph is built, the benefits in terms of accessibility and usability might outweigh the initial investment. And comparing to databases, tells me R1, knowledge graphs offer more flexibility in querying the relationship. SQL databases require joins, or old friends, which can be computationally expensive with complex relationship. Graph databases, which underpin knowledge graphs, use graph traverse techniques that are more efficient for such queries. Another point is interoperability. Knowledge graphs often use standards like RDF or OWL, which facilitate data exchange and integration across different systems and domains. This standardization isn't typically present in traditional databases or text documents, making knowledge graphs more versatile in heterogeneous environments. So you see, in terms of AI and machine learning, knowledge graphs provide structured data that can enhance our LLM models. For instance, embeddings from knowledge graph can capture relational information that text-based models might miss. This can improve the task like entity recognition, recommendation system, and more. So comes now R1 to its own conclusion, which is absolutely amazing for an AI machine. So R1 tells me, synthesizing all these points. Now, knowledge graph offer structured, interconnected data that enhance machine understanding, enables complex queries, supports inference runs, improves semantic search, and integrates diverse data sources. While text documents and traditional databases have their strength, of course, knowledge graph fill the niche where the relationship and the context are paramount, providing a tool that bridges human-readable information and machine-actionable data. This is the reasoning process how R1 understands my question, why do we need knowledge graph? Why is it so important in the future of AI if we integrate knowledge graph? And from this, I learned almost more than the original answer. So let's have a look at the original answer. And you know what? It's such a pity that OpenAI with O1 does not have this reasoning process that takes 43 seconds. We are locked out here of the learning and the analysis of an AI that honestly for me is more valuable than now the official result. But anyway, let's have a look now at the official result by R1. Structured versus unstructured data. So we have textual information. It is human readable but unstructured, making it challenging for machines to parse relationship and context. Databases are structured but rigid, requiring predefined schemas that limit the flexibility in capturing dynamic relationship. And now knowledge graph. They combine the structure with flexibility, using nodes, entities, and edges the relationship to model interconnected data, enabling both human and machine understanding. What an absolute beautiful answer to explain structured and unstructured data for two different user groups, humans and machines, for advanced reasoning. Key advantages of knowledge graph. Nice. Semantic context and relationships. Knowledge graph explicitly define relationships, like Einstein influenced Niels Bohr, enabling machines to understand connection without relying on implicit textual cues. Ontologies and taxonomies standardize the meanings, enhancing the interoperability across different domains. Inference and reasoning. Knowledge graphs support logical deductions, like inferring here A is a grandparent of C from parent-child relationship, automating insights that require human effort in text. The query efficiency. Graph traversal outperforms SQL joins for complex relational queries, like find scientists who work in both biology and AI. And the query efficiency is here also noted. It enables multi-hop reasoning with knowledge graph. Find companies founded by Stanford alumni in renewable energy. Another benefit is semantic search for knowledge graph. Moves beyond keyword matching to interpret the intent. French painters influenced by Japanese art retrieves Monet via knowledge graph relationship, not just the text mentions. Scalability and adaptability. New nodes and relationships integrate seamlessly without a schema redesign. Idea for evolving data. Machine learning graph embeddings enrich the models with relational context, improving tasks like a recommendation system. And then there's a point that's really nice. Comparison to alternatives. So we have knowledge graph versus text documents. The pro of text. Natural language captures the nuances and it's easy for humans to create and read. The cons of a text. Machines struggle with the human ambiguity, requiring here complex pipelines that are error-prone and computationally intensive. Knowledge graph versus traditional databases. The pro of a database, efficient for transactional queries, inventory management. The con of a database, schema rigidity limits our ad hoc exploration of the relationships. And a knowledge graph versus graph databases. The pro of a graph database, it is optimized for relationship-heavy queries, great. And the pro of knowledge graphs, layer semantic meaning atop graph structures, enabling cross-domain integration and reasoning. I like the simplicity, but the heavyweight answer, this is just providing enough information for me to understand it, even if I would understand nothing about the topic. It also gives me the limitation on knowledge graph. Requires curation of the entities of the relationship, often involving manual effort or some advanced system. And for the data quality, there are inaccurate links or outdated information that can propagate errors. So the scientific judgment by R1 now is knowledge graph are not a replacement for text or databases, but a complementary tool. They excel in scenarios where relationship, context, and interoperability are critical, such as integrating heterogeneous data, powering intelligent assistant, and enhancing AI with explainable reasoning path. What a beautiful explanation. So while books and database remain vital, knowledge graph bridge here the gap between human-centric text and machine-centric data structures, unlocking nuanced insight at scale. And their value grows as the data complexity increases, making them indispensable in the era of AI and big data. This is all that I need to go on, since now I understand the importance of knowledge graph in the future of AI compared to databases or long text documents. And this is the video for today. It was so fun preparing this video. It was so interesting to learn of this. Sometimes I feel I need a second brain because I have so many ideas based just on reading the paper. But if you found it interesting, if you said, hey, I want to try this out, why not subscribe? And I see you in my next video.